Greetings to all who are watching this video. This part is part of the Liquid Propellant Rocket Engine Tests course from the Department of Aircraft Engine Theory at Samara University. In this course, you will learn why tests are conducted, how to organize them, what tools are needed to conduct them successfully and safely, how to process experimental results to get the most accurate information possible, how to get the desired result with the minimum number of tests, and much more. This is the fourth part of the course. In it, I will give you an overview of experimental planning methods. Two types of experiment are distinguished according to the type of impact on the test object. An active experiment is an experiment in which the research intentionally influences the object under study. Such an experiment can be planned. A passive experiment is an experiment without any intervention in the process. Passive experiments involve the accumulation of information in normal operation, but this is time-consuming and costly. With the active, purposeful intervention in the process, an accelerated accumulation of information is possible. The program for intervention is set by the plan. The planning method itself may vary depending on the type of task, but the general principle of intervention remains. The mathematical theory of experimental planning refers to the science of making economical experimental designs that simultaneously extract the greatest amount of information about the object of study. The way experiments are conducted, the way experimental data are processed and used to optimize production process, as well as engineering calculations. The theory of experiment planning began with the work of Ronald Fisher in the 1930s, which he used to solve agrobiological problems. The sequence of an active experiment is as follows. Schematics of the research are developed, meaning experiment planning is carried out. The planning of experiments usually requires either the construction of the regression model of the process at the lowest cost and with the necessary accuracy, or determination of its optimum conditions. The experiment is carried out according to a plan drawn up in advance by the researcher, meaning the active experiment itself is carried out. Measurement results are processed, analyzed, and decisions made. Thus, experiment planning is a procedure for selecting the conditions and number of experiments necessary and sufficient to solve the problems with a given accuracy. The use of experiment planning theory ensures minimization of the number of experiments required, variation of all factors at the same time, selection of a clear strategy, minimization of experimental errors through the use of special checks. To illustrate some of these points, consider an example of a good and a bad experiment. Consider the example of weighting 3 objects, A, B, and C on scale. The first approach involves an empty weighting to determine the 0 point of the scales, and then sequentially weighting each of the samples. This is an example of a traditional one-factor experiment. Here, the researcher studies the response to the behavior of each factor separately. A traditional weighting scheme is shown in the table on the left. When a sample is placed on the scale, the table shows +1. When it is not on the scale, it shows -1. The mass of each object is estimated only from the results of 2 experiments, the one in which the object under study was placed on the scales and the blank experiment. Then the mass of the is object is equal to this. The weighting error is assumed to be independent of the quantity being weighted, additive and having the same distribution. Then the dispersion of the mass measurement of the is object is this, where sigma is the dispersion of any weighting. Let us now conduct this experiment according to a different scheme, given by the planning matrix in the table on the right. In the first 3 experiments, objects A, B, and C are weighted in sequence, and in the last experiment, all 3 objects are weighted together. The mass of the object A will be given by the formula. The masses of the objects B and C are found using similar formulas. In this formula, the mass of the is object is not affected by the masses of other objects, because the mass of each element enters the formula twice with different signs. Let us now find the dispersion of the is object associated with the weighting error. We see that the planning experiment results in half the dispersion of the weighting results compared to the one-factor experiment, although in both cases it took 4 experiments each to weight 3 objects. So, what is the reason for doubling the accuracy of the experiments? In the first case, the experiment was set up so that each mass was obtained from only 2 weightings. The second scheme can be called a multi-factor scheme, because here all the factors are operated so that each mass is calculated from the results of all the experiments at once. This is the main reason why the dispersion is halved. This example shows that the use of experimental planning theory can be one way of significantly improving the effectiveness of multi-factor experimental studies. A liquid propellant rocket engine is a technically complex, environmentally and human hazardous and costly product. The use of experimental planning methods to select optimal design options, refine it, determine and validate its main characteristics, and evaluate its reliability can significantly minimize time and material costs and increase the safety of the result. However, the use of experiment planning methods in liquid propellant rocket engines is complicated by the fact that a large number of both external and internal factors influence engine parameters and performance. Modern methods of experimental planning do not require the influence of each factor to be determined, one by one, but make it possible to find the optimum conditions for implementing the process, assess the performance of the engine, its elements, etc., when several influencing factors are varied simultaneously. They also make it possible to develop a rational sequence of operations when preparing and conducting experiments, analyzing the results and making decisions based on the materials obtained. In the study of complex systems with insufficiently clear internal connections, such as LPRE, a flight recorder model is usually used. The Y errors represent the output numerical characteristics called target functions, optimization parameters or flight recorder output parameters. These can include thrust, specific thrust impulse of the liquid propellant rocket engine, parameters determining its performance, pressure in the combustion chamber, etc. The way in which the flight recorder operates, X, is called the factor or input parameters. These can include all the external and internal factors that influence the main output characteristics of the LPRE. For example, regulation of propellant or oxidizer flow rate, changes in the engine output parameters. Each factor has a definition area, which is understood as the totality of all values it can take depending on the operating conditions. The scope can be continuous or discrete. Factors are divided into quantitative and qualitative. The latter may include, for example, different fuels, etc. The factors are subject to the following requirements. The factors must be controllable, meaning it must be possible to set and maintain their value during the experiment. Factors must be operational. This requirement is fulfilled if the sequence of operations, by which specific values or levels of factors are established, is clearly defined. The accuracy of factor measurements should be as high as possible. A combination of factors has additional requirements, such as compatibility, meaning all combinations must be realizable and safe. The independence of factors in combination, meaning it should be possible to fix a particular factor at any level, regardless of the levels of other factors. If the number of factors is large, this leads to an increase in the number of experiments. Therefore, if the number of factors is greater than 7, it is advisable to remove unimportant factors. This is done either on the basis of preliminary theoretical calculations or on the basis of experience. At the same time, if the influence of any significant factor is not taken into account, this may lead to errors in determining the target function. If the aim of the experiment is to determine the optimum conditions for the process, then a target function corresponding to either a single parameter or the sum of several parameters should be selected. If the aim of the experiment is to describe the process under study mathematically, it is desirable to obtain a target function for the whole set of the parameters characterizing the investigated object. The target function has the following requirements. It must be quantitative. It must be expressed in numerical form. If there is no way of quantifying the result, a ranking approach is used. The function must be single-valued, meaning one value of the target function must correspond to a specific set of input factors. The function must be effective. It must actually assess the effectiveness of the system. The function must exist for all possible states of the system in the area under study. A mathematical model of the object of study is used when solving the problem of planning an experiment. This refers to the equation linking the target function to the factors. Such a function is called a response function. The values y and x can be understood as both the parameters of the liquid propellant rocket engine and their deviations. Constructing a mathematical model or determining the response function is the most important experimental task of the method, because it can be used to predict the values of the function, meaning the response in states that have not been studied by the direct experiment. The model of the process under study refers to the response function. Model selection is the selection of the type of function, meaning defining this equation. If the type of function is known, an experiment is initially planned and conducted to estimate the coefficients of this equation, regression coefficients. The main requirements for a model are adequacy and simplicity. Adequacy is the ability to predict the results of an experiment in some domain with a given accuracy. In planning an experiment, polynomial models are usually used, which are relatively simple, convenient and well developed mathematically. The polynomial models for the two factors are as follows. Polynomial of the zero power, polynomial of the first power, polynomial of the second power, and polynomial of the third power. The power of the polynomial should be chosen as small as possible. The smaller it is, the fewer the coefficients in the equation, and therefore the fewer experiments are needed to determine them. The response surface is a geometric equivalent of the response function. For clarity, consider a flight recorder with two factors. These can be understood as changes in parameters characterizing thrust control and fuel component ratios. The corresponding response surface is shown in the upper figure, and the projections of its cross-sections on the plane in the lower figure. With more factors, the geometric clarity is lost. If a design optimization problem is being solved, the main requirement for the model is that it can be used to predict the direction of the fastest improvement of the parameter in question. This direction is called the gradient direction. This requirement is easiest to fulfill by using the first power polynomial. A linear model will be adequate if the sub-area in the factor space is chosen correctly. The latter is possible because there is almost always a surrounding area of any point in which the linear model is adequate. In some cases, it is necessary to construct an interpolation model which gives the result of the required accuracy over the whole given domain. However, a linear description of the response surface may not be adequate. Therefore, we have to increase the order of the approximating polynomial. But for most practical tasks, satisfactory accuracy can already be achieved by using polynomials of the second power. The design of the experiment depends on the type of model adopted, the number of trials and the number of special requirements for the descriptive properties of the model. A preparation phase must precede the conduct of the experiment. It begins with the collection of primary information about the object of study. A primary information can be obtained from previous studies. This information gives an indication of the optimization parameter, the factors, the best process conditions, and the nature of the response surface, meaning it gives an indication of the degree of influence of the factors on the target function. Based on the primary information, a local area of factor space is selected for conducting the first series of trials. Depending on the order of the model taken, a distinction is made between first-order and second-order plans. First-order plans are called two-levels plans because the factors in these plans vary at two levels. Second-order plans involve varying factors at three levels and are therefore called three-level plans. If all factors under plan vary at the same number of levels, they are called symmetric. First-order plans allow an experiment to find an equation of regression containing only the first degrees of the factors and their products, and second-order plans allow an experiment to find an equation of regression containing the second degrees of the factors. The most widely used are complete factors plans of type 2 in the power of m, in which each factor varies at two levels and a complete set of two combinations of factors levels is implemented. Based on primary information, the values of factor levels are established, which correspond to the best result of the optimization parameter. These levels are taken as initial ones when constructing the experiment plan and are called the main zero levels. The upper and lower factor levels are established by adding to or subtracting from the base level a number L, called the factor variation interval, where these are the maximum and minimum values of factor I, respectively. The interval of variation should, on the one hand, be larger than the measurement error of the factor value, and on the other hand, it should be restricted above and below, so as not to exceed the factor's area of definition. It is customary to consider the interval of variation narrow if it doesn't exceed 10% of the factor's area of determination, not more than 30% medium, and in other cases wide. Since the factors affecting the object under study are not uniform and have different values and units, they should be reduced to a common system of calculation by converting from natural values of the factors to coded values. The upper level +1, the lower level -1, and the main level 0. For factors with a continuous area of definition, a transformation is used, where x is a factor-coded value, this is a real natural value, and this is the actual value of the factor at level 0. The condition of the experiment can be written in the form of a table, where the rows correspond to the different trials and the columns to the values of the factors. These tables are called planning matrices. As mentioned earlier, an experiment in which all possible combinations of factor levels are realized is called a complete factor experiment. The number of trials required for such an experiment is this, where m and q, respectively, the number of factors and the number of their levels. If two factors are varied at two levels, a complete factor experiment of n equals to 2 in the power of 2 is implemented. The table shows the planning matrix for the experiment, and the figure gives its geometric interpretation. The 2 in the power of m factorial experiment has a number of properties that simplify the mathematical processing of its results. Symmetry of the matrix relative to the center of the experiment. The algebraic sum of the vector column elements of each factor is 0, except for the column corresponding to the free term, where I is a factor number and j is a trial number. The normalization property, the consequence of which is that the factors in the matrix are given by the levels +1 and -1. The sum of the squares of the elements of each column equals to the number of trials. Orthogonality, according to which all regression equation coefficients are independent of each other. The scalar product of all vector columns, sum of the products of any two vector columns of the matrix is 0. Rotatability, circular symmetry, which ensure the same accuracy in the predicting the target function in any direction. In each series of experiments, the sequence is randomized. This, to a certain extent, eliminates the bias and subjectivity of the researcher, as well as the systematic errors, such as heating or cooling of the units and other factors in the study of the process. Complete factor experiment 2 in the power of 3 will have 8 experiments. Its matrix is shown in the table. Geometrical interpretation of complete factor experiment is a cube, Coordinates of its verticals 1 to 8 are given by conditions of experiments. For a linear model with a 2 in the second power complete fact experiment, the polynomial is this. The coefficients of the regression equation BI are determined by the least squares method, which minimizes the sum of the squares of the deviations of the experimental values of the response function yj's and the values of the ypj's determined by the model. Using the properties of a complete fact experiment, we obtain the coefficient of the regression equation in general terms. According to the planning matrix of the experiment, we obtain the coefficients in the partial form. Consequently, any coefficients in the regression equation are determined by the scalar product of a column yj's by the corresponding column xij's. Similarly, coefficients are determined if linear interactions are considered in the regression equation. Note that all linear coefficients are independent, so each coefficient describes the role of the relevant variable in the process or the strength of influence of the factors. If the coefficient has a plus sign, the response increases as the value of the factor increases, and if it has a minus sign, the response decreases. Factors with coefficients that are insignificantly different from 0 can be removed from the equation, as the influence of the response parameters will be attributed to experimental error. To simplify the calculation of the coefficient, it is convenient to introduce a column vector of the dummy variable x0, which takes values +1 in all experiments into the planning matrix. Then the linear model has the form, and all coefficients are calculated according to the above formula. The complete fact experiment also contains information about nonlinearity due to the interaction effects of factors. The presence of interaction effects means that the effect of one factor depends on the level of another factor. In order to quantify the interaction effects, it is necessary to obtain a vector column product of factors. For the complete fact experiment, 2 in the second power, the planning matrix for the interaction effect is shown in the table. The model in this case has the following form. The interaction coefficient B12 is calculated as usual according to the formula. Since a particular value of the response function obtained in an experiment is random and has some error, trials can be repeated for each row of the planning matrix to improve reliability and reduce the impact of the experimental error on the value of the optimization parameter. Such trials are called parallel or duplicate ones. If trials are repeated, the average value of the response function is used. If the number of trials in matrix rows is unequal, its orthogonality is broken, and the formula for the calculation of regression coefficients cannot be applied. In this case, more complex dependencies are needed. The planning and implementation of a complete fact experiment is done in the following sequence. Selection of the optimization parameters, influencing factors and level of factor variation. Factor coding. Complying an experiment planning matrix. Randomization of trials. Trial conduction. Mathematical processing of the results of the factorial experiment, including checking for uniformity of dispersions between parallel trials and reproducibility of the results. Calculation of the mathematical model coefficients, regression equations, their errors and significance. Checking the adequacy of the mathematical model. The mathematical processing of the results of the factorial experiment is carried out in the following sequence. First, the dispersion of parallel trials, or in other words, the line-by-line dispersion, is determined, where L is equal to 1.2 to n, parallel trial number. Second, the next step is to test the uniformity of the line-by-line dispersion using the Cochrane criterion. The Cochrane criterion is a ratio of the maximum line-by-line dispersion to the sum of all dispersions. If the calculated value of the Cochrane criterion is less than its table critical value, for the number of degrees of freedom f1 equals to n minus 1 and the number of trials f2 equals to n, at a chosen significance level, usually take 0.05, then the results do not contradict the hypothesis of uniformity of dispersions, and the generalized averaged dispersion of reproducibility can be applied at the following stages of the analysis. Otherwise, when the calculated value of the Cochrane criterion is larger than the tabulated value, the dispersions are not uniform, and hence the observed experimental results YJL either characterize different test objects or the trials are not correct. In the third step, the dispersion of the optimization parameter or dispersion of the reproducibility of the experiment is determined. This value is calculated as a quotient of the sum of the line-by-line dispersions divided by the number of trials in the planning matrix of the experiment N. Here, F2 equals to N is the number of degrees of freedom for determining the dispersion of the optimization parameter. The use of such a formula is possible if the number of parallel trials is the same in the whole planning matrix of the experiment. In step 4, the statistical significance of the mathematical model coefficients is checked. A coefficient is considered significant when its absolute value is greater than the confidence interval, where T is a student's criterion, and this is a root mean square error in determining the regression coefficients calculated by this formula. The meaning of this equation is that the absolute value of the coefficient must be t times greater than the error in determining it. Statistical insignificance of a coefficient is interpreted as a lack of influence of the relevant factor in the studied intervals of its change. Such coefficients are excluded from the mathematical model. In the last step, the adequacy of the mathematical model is checked using the Fisher criterion, which is the ratio of the adequacy dispersion to the reproducibility dispersion. The adequacy dispersion is determined by this formula, where these are the values of the optimization parameter in jth trial, respectively determined experimentally and calculated from the mathematical model equation. K is the number of coefficients in the model, including the free term. The calculated Fisher criterion is then compared with the tabulated one. If the condition is fulfilled, the mathematical model is considered adequate. Reasons for inadequate models can be insufficient model order, poor choice of variation interval, large reproducibility dispersion, large number of factors that have no significant effect on the response function. To conclude this section, it should be noted that if the number of trials n is equal to the number of coefficients k, to check the adequacy of the model, several parallel trials at the main level should be carried out and the average value of y0 determined. If the difference obtained, y0 minus b0 is less or equal to 0.5, the model can also be considered adequate. It is reasonable to use a complete fact experiment when the number of factors does not exceed 5. Otherwise, the number of options for variation becomes excessively large, and the practical implementation of such an experiment becomes difficult. If we neglect higher order interactions, it is possible to obtain a mathematical model with a smaller number of trials, implementing not the whole CFE plan but only a part of it, a fractional replication. The number of trials in a complete fact experiment exceeds the number of linear model coefficients to be determined, and this excess will be the higher the more the number of vectors is. Therefore, it is possible to reduce the number of trials by refusal of information about interaction facts of factors, which will be the less the closer the actual model is to the linear one. Thus, fractional replication is part of a complete fact experiment in which linear effects are equated with the interaction effects. An experiment that implements a part of a complete fact experiment is called a fractional fact experiment. The fractional replication is denoted by this, where m is the number of factors and p is the number of interaction effects. The notation of some fractional replications and the number of trials needed to implement them are shown in the table on the right. This table shows that the use of fractional replications allows a significant reduction in the number of trials and that their usefulness increases as the number of factors increases. A saturated factor experiment is an experiment in which the number of factors is one less than the number of trials, rows of experiments. Otherwise, it is called an unsaturated experiment. In the fractional factor experiment, different fractional replications can be chosen. If choosing fractional replication like this, there are only two half-replication solutions. Then choosing this fractional replication. It already allows for 8 half-replications, solutions of the FFE, presented in the slide. Possible fractional replications from these are shown in the table. The efficiency of the different replications is not the same. It is used to estimate the resolution determined by the analysis, using characteristics such as determinant contrast and generation ratio. The determinant contrast is the product of any vector columns where all the elements of the resulting U vector column have the same sign. If all signs are positive, the determinant contrast is given a symbolic value of +1, and if negative, -1. An example of determinant contrast is shown in the table. The determinant contrast is used to set up a blending system of linear effects with interaction effects. To determine which effects, double, triple, etc., are mixed with a given linear effect, multiply both parts of the determinant contrast by this linear effect. If the determinant contrast is this, then we obtain this, as it's always x in the power of 2 equals to 1. A generating ratio is a ratio that shows which of the effects a given linear effect is mixed, meaning the ratio obtained above is a generating ratio. For example, the linear effect of x1 is mixed with the paired effect of x2 and x3. For example, this where beta I is the actual value of the coefficients needed. The generating ratio allows us to estimate the resolution of a fractional replication. The higher the order of interactions with which the linear effects are mixed, the higher the resolution of the latter will be. This is explained by the fact that interactions of higher orders, triples in our case, are more often equal or close to zero than interactions of lower orders. For the 8 solutions possible with the choice of half replication, solutions 7 and 8, which are called the main ones, have the highest resolution power. In the absence of a primary information on interaction effects, fractional replications with the highest resolution should be chosen. Select the main. In some cases, a first-degree polynomial is not sufficient to describe the response function. For most practical applications, a good approximation to a nonlinear response function is provided by the second-order polynomial model, shown on the slide. To determine the values of the coefficients of such a model allows a complete factor experiment 3 in the power of m, as the number of levels of variation of the factors must be 1 more than the degree of the approximating polynomial. The number of possible combinations of trials in a complete factor experiment is n equals to 3 in the power of m. In this case, the complete factor experiment contains too many trials. So at m equals to 3, there are 27, and the number of factors by are 10. At m equals to 5, the number of trials are 243, and the number of factors bi are 21. In this connection, it is not only difficult but also unreasonable to carry out CFE for plans of the second order. Such factorial experiments are hardly ever carried out in research on LPREs due to the large number of trials. A large number of second-order plans have now been developed which are more economical than complete factor experiments. The most widespread application in the study of the properties of nonlinear models are composite plans, with linear plans serving as a core. Depending on which points are added to this first-order plan, composite plans with different properties are obtained. Symmetric second-order central compositional plans are constructed by adding to the original two-level linear plan core containing Ns equals to 2 in the power of m points with these coordinates, and 0 central points with coordinates, and these is axial so-called star points located in pairs along coordinate axis and distance from the central point, called the factor leverage. The magnitude of the factor leverage and the number of trials in the center of the plan N0 depend on the type of composite plan chosen. The total number of trials in the experiment is equal to the sum of the points. A geometric interpretation of the central compositional plan is shown in the figure. The composition plan for m equals 2 and n0 equals to 1 is shown in the table below. Similarly, experiment plans are made for more factors. Having analyzed the second-order compositional plan shown in the table and on the previous slide, we can conclude that this matrix of the experimental plan is non-orthogonal. Recall that the orthogonality property of the matrix allows the regression equation coefficients to be independent of each other. New variables for quadratic effects are introduced to make the matrix orthogonal. Compositional plans can be easily reduced to orthogonal ones by choosing the factor leverage. The table on the left shows the value of the factor leverage for different number of factors m and number of trials at the center of the plan N0. In particular, the orthogonal plan of a second order for m is 2 and n0 is 1 is shown in the table on the right, and its geometrical interpretation is shown in the figure below. The rectangular or quadratic experimental plan for the second-order model shown in the figure and table on the right is workable, although slightly excessive: 9 trials to determine 6 coefficients. With 3 excess trials, it allows the random errors to be averaged and their nature to be estimated. It should be particularly noted that the coefficients of the regression equation obtained with second-order orthogonal plans are determined with different accuracy, while first-order orthogonal plans provide the same accuracy of coefficients, meaning, although the plan considered above is orthogonal and provides independence of coefficients determination, it is not rotatable. Another possible approach to finding a nonlinear response function is to use a second-order rotatable composite plan. It is distinguished by the following features. The value of the factor leverage is chosen from the ratio, where m is the number of factors and p is the number of factor interaction effects, or in other words, fractional replication. P is 0 for a complete factor experiment, p is 1 for a half replication CFE, and p is 2 for the CFE quarter replication. The number of points in the center of the plan N0 increases according to the number of independent factors at the core of the plan, as illustrated in the table at the top right. The choice of the value of the factor leverage can be explained using the example of a second-order rotatable planar matrix for m is 2, shown in the table below, with the placement of the points of this plan shown in the figure on the left. To ensure rotatability of points 5, 6, 7, and 8, it is necessary to remove them from the center of the plan at a distance a is 1.414 times greater than the distance of points 1, 2, 3, 4 from axis x1 and x2. As a result, all points of the plan appear to lie in a circle. Taking into consideration influence of random error in the center of the plan on response function, it is recommended to perform at this point of the plan not one but some double trials, 9 to 13 trials in this case, for averaging of results and for statistical analysis of the results of the experiment as a whole. However, the second-order rotatable planar matrix is non-orthogonal. The condition of non-orthogonality was discussed on the previous slide. Therefore, if any of the quadratic effects is found to be insignificant, once it has been eliminated, the regression equation coefficients must be recalculated. If the second-order model proves to be inadequate, the experiments should be repeated over a small interval of variation in the factors, or the center of the plan should be moved to another point in factor space. In case where the model is still inadequate, it is recommended that we move to third-order plans. An experiment that solves the problem of determining the numerical values of the factors at which the response function, output parameter and optimization parameter reaches an extreme value, maximum or minimum, is called an extreme. An extreme experiment consists of solving an optimization problem and is formulated as follows. The goal is to determine the coordinates of the extreme point of the response surface at which the response function is maximal or minimal. A graphical interpretation of the optimization problem for two factors x1 and x2 is shown in the figure. Point A corresponds to the optimum values of the factors x1 with a star and x2 with a star, providing a maximum of the response function ymax. The closed lines in the figure characterize the constant level lines and are described by the line equation. The well-known trial and error method, in which factors are changed based on experience, intuition, or at random, with the usually large number of factors in process research, is often ineffective because of the very complex dependencies of the response function on the factors. Search engine optimization methods require significantly fewer experiments and lead to a desired result more quickly, as a stepwise variation of the factors is done purposefully according to a specific plan. Such methods of optimization are iterative, whereby the entire process is broken down into steps. At each step, a number of trials are performed, and it is determined how to change the factors affecting the process in order to obtain an improved result. At each step, the information obtained is used to select the next step. Many stepwise optimization methods have been developed. In our course, however, we will consider only some of them, the effectiveness of which in the industrial and laboratory experiments has been confirmed in practice. The following search engine optimization methods. The method of per-coordinate optimization, Gauss-Seidel method. Steepest ascent method, Box-Wilson method. The simplest method of experiment planning. The simplest method of optimization is the method of per-coordinate optimization, Gauss-Seidel method. The essence of the method is as follows. An arbitrary point M0 with corresponding coordinates is selected from the factor definition area. The search for an optimum is carried out by varying each factor in turn, first varying one factor, for a two-factor experiment x1, while fixing the other factors. For a two-factor experiment x2 is constant, until the response function stops increasing or decreasing, point M1. Then another factor is changed, for a two-factor experiment x2, while holding the other factors constant. For a two-factor experiment x1 is constant, and then the procedure is repeated. The method of per-coordinate optimization is quite simple, but with a large number of factors it takes a considerable number of trials to determine the coordinates of the optimum of the response function. Besides, for some dependencies, y equals to f from x1, x2 to xn, this method can lead to false results, reaching a local minimum. The figure illustrates one such special case, where alternating changes of each of the factors in either direction along coordinate axes x1 and x2, the solution results in a false extreme located at point A1, with coordinates x1 and x2 with a line, while the actual value of the maximum of the response function ymax is at a point A with coordinates x1 with a star and x2 with a star. This method has received limited use. Therefore, consider more advanced methods. It is known that the shortest path to an extremum is to move along the gradient, meaning perpendicular to lines of equal level where the response function takes constant values. Therefore, when optimizing the process, it is advisable to move in the direction of the fastest increasing response function, in the direction of the gradient of the response function. There are various modifications of the gradient method. One of them is the steepest ascent method, Box-Wilson method. The essence of this method is that the stepwise movement is carried out in the direction of the fastest increasing gradient of the response function. Grad y equals to f from x1, x2 to xn. However, the direction of movement is not corrected after each subsequent step, but when a partial extremum of the response function at some point m0 is reached at that direction. A geometric explanation of this method for a two-factor experiment is shown in the figure. To move along the gradient, it is necessary to change the factors in proportion to their regression coefficients and in the direction corresponding to the sign of the coefficient. The search moves in this direction until a local maximum is found, point m1. At the point of the latter, one finds a new gradient direction, direction m1n, by again performing a CFE or FFE. And then the procedure is repeated. The arrows in the figure shows the trajectory towards the optimum. The algorithm of the Box-Wilson method comes down to the following sequence of operations. First, planning and setting up a complete or fractional factor experiment in the area of point m0 as the center of the plan. The coordinates of the individual trials for the two-factor experiment correspond to points 1 to 4. From the results of the CFE or FFE, the coefficients of a linear mathematical model can be calculated to determine the directions of the coefficient. The gradient of the response function at this point is determined by the formula on the slide, where these and these are unit vectors in the direction of the coordinate axis. Second, calculation of the product, where these is the intervals of variation of the factors. Third, selection of the base factor, at which this is achieved. Fourth, selecting a basic steep ascent step for the base factor HA. The choice of the base step is based on available or primary information or on the experience of the researcher. Too small pitch would require a significant number of trials in moving towards an optimum, while large pitch creates a risk of overshooting the optimum region. Fifth, calculating the pitch changes of the other factors using the expression. Sixth, drawing up a gradient movement plan. To do this, the coordinates of trials 5, 6, 7, 8, 9 are found according to the determined values of the factor pitches and their successive algebraic summation with the main level at the point. Some of these trials are carried out as the mental ones. A mental trial consists of obtaining predicted calculated values of the response function from a linear regression equation, which reduces the volume of real trials, meaning increases the speed of progress towards an extremum. In a mental experiment, translation of the coordinates into a coded form and substituting them into the object model equation should confirm the actual increase of the response function y. Usually, real trials at the beginning of the movement from the base point along the gradient direction are put into 2 to 4 mental trials. Other trials are realized in practice by determining a sequence of values of y in the direction of the gradient. From the experimental data, the position of the local extremum, point M in the figure, is found. Seventh, in the area of the local extremum, a new series of trials, a complete factor experiment and fraction factor experiment, is performed to determine new values for the regression equation coefficients of the new gradient direction, direction M1 n. The procedure is then repeated until a local extremum is reached, and so on until the coordinate area of the maximum response function, which is called the near stationary area, is determined. An indication of achievement is the statistical insignificance of the coefficients bi. In the near stationary area, interaction effects and quadratic effects become significant. Here, it is required to change from FFE to CFE, and if this is not enough, to change from the first-order experimental plans to the second-order plans. The simplex planning method uses a special simplex experiment plan and refers to gradientless methods of finding the optimum. A simplex is the simplest convex polyhedron formed by n+1 vertex in the dimensional space, which are connected by straight lines, where m is the number of factors. In this case, the coordinates of vertex of the simplex are the values of the factors in separate trials. In the two-factor m+1 = 3 space, the simplex is any triangle. In the three-factor, in the three-dimensional space, it is a tetrahedron, etc. A simplex is called regular or proper if all distances between its forming vertex are equal. Equilateral triangle, regular tetrahedron, etc. After constructing the initial simplex and conducting trials, the results are analyzed and the vertex of the simplex at which the smallest worst value of the function has been obtained is selected. To move to the optimum maximum, the new point, which is the mirror image of the point with the smallest result with regard to the opposite edge of the simplex, must be tested until the almost stationary region is reached. To find the optimum minimum, the highest value of the simplex vertex is found. The left figure shows the geometric interpretation of the simplex method for the two-dimensional case. After trials 1, 2, and 3, trial 3 is the worst. The next trial is placed at point 4, which forms a new proper simplex with point 1 and 2. The results of test 1, 2, and 4 are then compared. The worst result is obtained at point 1, so it is replaced in the new simplex by the mirror image, point 5, and so on until the near stationary region is reached. Note that although the path is a zigzag one, the total number of trials needed to reach the optimum region may be small due to the fact that m+1 trials have to be performed only at the beginning, and each step is followed by only one additional trial, whose conditions are chosen based on the previous results. The choice of the size and position of the simplex is arbitrary. To construct the initial simplex shown on the right figure, the value in each trial of the initial simplex is determined by the formula given on the slide, where x, I, 0 coordinates of the center of the initial simplex, delta x, y factor variation interval, c, I, j coded value of the is factor for the jth trial, selected from the numerical matrix for simplex planning given in the table. The coefficients ki and ri are determined using the ratios below the table. As an example, let's make an initial simplex plan with the following initial data. Coordinates of the center of the initial simplex are these. Intervals of variation of factors are these. The calculation of the coordinates of the three trials is shown on the slide. The coordinates of the simplex calculated by the above relations are shown in the figure. The formula is used to determine the experimental conditions at the reflected point, coordinates of the new simplex vertex, where this is the coordinate of the new point, new vertex of the simplex for the ith variable. This is the coordinate of the point to be replaced, coordinate of the worst response vertex before it is discarded. And this is the average of the coordinates of all vertices in the simplex except the one to be replaced. The following criteria are known for ending the process of successive reflection of the worst vertex and setting up the successive trials in new vertex. First, the difference in the values of the response function at the vertex of the simplex becomes smaller than a predetermined value. This means that either the almost stationary region near the optimum is reached, or the surface area y equals to f from x1, x2 to xn is constant is reached as a plateau. In this case, by additional trials away from the simplex, one should make sure that there are no other areas with more significant curvature of the surface, y equals to f from x1, x2 to xn, and take the magnitude with the extreme value of the response function as the point of optimum. Second, the reflection of any of the vertices of the simplex after a single swing leads to its return to the former position. There is a reason to believe that the simplex covers the optimum point. The cyclic movement of a simplex around one of its vertices over more than a few steps A similar situation occurs when the desired optimum is located within the area covered by the circulating simplex. In cases 2 and 3, it is recommended to reduce the size of the simplex, meaning the distance between the vertex, and continue the search until the desired specification of the coordinates of the desired optimum. The simplex method algorithm, described above, is relatively simple. It is quite effective even for minor errors in the definition of the response function, but it is not fast enough. There is a modification known as the deformable simplex method, which speeds up the process of finding the optimum by using the information accumulated at the previous steps at this stage. The essence of the deformable simplex search method is that by reflecting the worst vertex relative to the center of gravity of the opposite edge, the size of the simplex does not remain constant, but it is deformed, stretched or compressed. That is the end of today's lecture. In it you have learned what planning an experiment is and why it is needed, and how to plan an experiment, what a complete fact experiment is, what a fractional fact experiment is, how to find the best combination of variant parameters in an experiment. I hope you have understood this lecture. If you still have any questions, comments, or if you find mistakes, feel free to let us know in the comments or private messages. And we will meet you in the next video lecture.